this is not a good example to show failure of the the theorem, because every pair, if you pick any two columns, they're linearly independent. It just so happens in this example. So you can't go wrong with this. You can always pick any two variables here and solve for the other two. In terms of the other two, I should say. Here's a different problem. I thought these linear problems were good to kind of see what's going on here without getting distracted in a multitude of e to the x's and sines and cosines and whatever else I might do to you. So here's 3 equations and 5 variables. The question is, so we expect to be able to solve for what? 3 of the variables in terms of the remaining 2. So if I can solve for, what's my notation? ZAB, in terms of x and y, I would need invertibility of this matrix. If I wanted to be able to solve for like the last 2 variables in terms, if I want to be able to eliminate the first 3 variables in terms of the last 2, I need invertibility of this thing, right? Right. Here there's exactly here there's some you can do, some you can't do. But I actually, the thing I have just covered up with the whiteboard, I actually worked that out here for a specific point. So I say, okay, so solve this equals to 24, 30, 42 for x, y, and z in terms of a, b. You can do that, right? So like, I just say this is equal to that. So I got partial g, partial x, y, z, x minus 1, y minus 2, z minus 3, because that's the point which gives you 24, 30, 42 I'm centering around is 1, 2, 3, 4, 5. Yeah, so 1, 2, 3, 4, 5. And so that gives me this matrix. I'm trying to solve for these, so then I just basically take this, put it to the other side, and multiply by the inverse of that. That solves for x, y, and z in terms of a and b. And here it is in glorious detail. Oh, and I even multiplied it out. Now, so there it is, x is in y and z in terms of a and b as a consequence of the invertibility of that particular sub-Jacobian. Of course, this is not the best way to solve this problem, right? You should just do row reduction and use techniques of linear algebra to solve it, but I wanted to showcase the method of the proof. All right. As Joe was saying, yeah, let's see, so it's, yeah, if I add this plus this gives me 2, 0 plus 2 is 2, 2 plus 1 is 3. So the third column here is the sum of the first 2, which means that this is not invertible. So I cannot eliminate y, z, and a in terms of, I can't solve for those as functions of the remaining variables, x and b. Can't be done. And I can't solve for, well, can I? I don't know. Is this one invertible? Oh, okay. So again, I cannot solve for x, z, and b as functions of a and y. So if you think about this in applications, we're all the time, here's the thing. In engineering and in physics, problems do not come to you telling you what's a function of what. Oftentimes when you model things, you just get this mess of equations. And there's really no distinction between the different letters in the equations. It's just an equation. And so what's a function of what? Mathematically, this is a very challenging question, generally speaking, but the implicit function theorem gives you some kind of path through the wilderness on this. Now sometimes there's some sort of like physical suggestion for why one thing is a function of the other. Like if you think about, for example, velocity. I always give this as an example. Is velocity a function of time, or is time a function of velocity, right? If I write down, v is equal to v naught, a constant, minus gt, easy like, aha, well, velocity is a function of time, right? But you could solve for t, right? T is equal to v minus v naught divided by, minus g or whatever. So is velocity a function of time, or is time a function of velocity? I usually tend to think it's probably better to think time is, velocity is a function of time. I don't think that the velocity of a material object controls time, or does it? I don't know. But this is my point, is there may be some sort of philosophical reason that one thing should be a function of the other, but in lieu of that, implicit function theorem tells you which subset of the variables in a given system of equations you can choose to write as functions of the other variables. And that is a powerful thing. Do I at least have some example here, which is, no, I don't have it. So I'm actually going to do the implicit differentiation next class. I'm not even going to do that this time. If you'll forgive me. I'm going to go back, and for the remainder of the time, I'm going to talk about the proof of the implicit function theorem in terms of the inverse function theorem. So here is the implicit function theorem in all of its glory. You have g, a function from Rm cross Rn to Rn, continuously differentiable on some open ball about the point AB, where g of AB is equal to k, a constant vector, right? And the matrix partial g partial y of AB is invertible. Then it's the case that we can find some differentiable mapping h from u to Rn, such that if we plug in y equals to h of x, we get g of x comma h of x equals to k for all x and y close enough to the solution that we're given. And moreover, the mapping h is the limit of a sequence of successive approximations, like so. This is a modified Newton's method for that thing we did. I'll probably talk about this another day in here when the time is right. By the way, the solution, the schedule I've written for this class is total nonsense. I'm pretty sure I'm going to push the test back a week, because you guys need some more time to figure out the homework before the first test. It's not reasonable, my current test date. And I'm probably going to remove those ambiguous lectures at the end and just kind of space the material out. I think we have enough in the topics I've actually listed. Probably after break. Yeah. After fall break. Well, you guys let me know about your other tests. We will work around the other classes. It's fine. It will not be an issue. We will make, I will make accommodations to. It won't be a problem. So I think last time I taught this class, I gave the students like a week to take the test. They could just pick a day in the week and take the test, and they agreed not to talk to each other about it, and it worked. So if we do that, it should work out. But I think I can trust you guys. Yeah, I think so. Can you trust each other? I don't know. If we don't have trust, what do we have? America. But pretty much. Let's see here. So the thing is to prove the implicit function theorem from the inverse function theorem, you have to invent a function which is from the appropriate space to the appropriate space that captures the same thing. And the trick is really, it's really this really neat trick, is you define a function f from Rm cross Rn to Rm cross Rn. Part of it's going to be the equation, the g function, the set of equations. And then you need something else to fill it out, right? So it's very simple. What you just do is you do f of x comma y. So you do x. So x is an m vector. This is an n vector, so you've got m plus n. And so there it is. You just do f of x comma y is x comma g of xy. That's the function. And the claim that we're going to show, it's very simple, to show that that function actually is having a invertible Jacobian at the point as a consequence of just assuming that partial g partial y is invertible at the point. Right, that's the condition. We need partial g partial y is invertible in order to solve for y as a function of x. Yeah. Oh, could I write g comma x? I mean, I could write g comma x. It would just be, it would create clutter. No, it has to be the x because this is m dimensional, this is n dimensional. This g is n equations. So this is actually an n vector. No, it has to be x because otherwise the counting doesn't work. But let me just go on here. It's is it continuously differentiable? Well, we're assuming that the derivatives of g are continuously differentiable at the point in question. The function x, so you have x comma y maps to x. Is that a differentiable function? You would very much like that question on your first test. I mean, yes, you can choose delta equal to epsilon, and I mean it's like. Anyway, that is in fact differentiable. Yes. So. You got it? Okay. So f prime of xy would be partial x partial f, partial y partial f, but that would be partial x partial x. So it's these submatrices. And of course, you can work through the details, but this is basically just the m by m identity matrix because x is going to x. And let's see here. Then you have partial x partial g, which you don't really, I mean, whatever it is, it is. We don't have any information about that except that the derivatives are continuously differentiable there. This is the zero matrix because there is no, x and y are independent variables here, right? And so that's 0 and this. And then so what's the determinant of this block matrix? It's the product of the determinants of the blocks. That's 1. This is non-zero by assumption, so this matrix is invertible. And it's continuously differentiable. Therefore, the function f satisfies the conditions for the inverse function theorem. And I can solve this I can solve for, let's see here. I can solve, oh, come on, where did I put it? So the inverse function theorem applies to the function at the point a comma b. That means I can find an inverse function which is continuously differentiable such that f of ab is equal to a comma g of ab is equal to ak. Well, here's more to the point. F inverse of f of xy is equal to xy. And on the other hand, f of f inverse of uv is equal to uv. So, what is this inverse function look like? Well, it's got, there are two components. The one is easy enough to see. Let's see here. It's just battling with notation from this point on out here. If you look at it and suffer the details here, they're not that complicated really, but f inverse of uv is going to be u because of the way f is defined. It's easy to find that part of the inverse, but the second thing is some function that I know exists, but I don't know the formula for h. But it turns out that's exactly the thing I need to solve the equation. So I have this h of uv, and so if I plug that back into here, I get f of u comma h of uv, but that's equal to u comma by the definition of the f function, that's u. The first thing goes to the first thing. The second thing gets fed into g, like that, g of x comma y. So I get g of u comma h of uv, but that's equal to what again? That's equal to v. But if you let v equals to k, all right, then there you have it. The h function is in fact the solution you're looking for. So you have the u variable. So h of little h is big H of u, which is fixed. and there's your local solution. This illustrates a general idea in math, which is to solve a problem where you have fixed variables. Sometimes if you let the variables be free and lift it to a higher dimensional problem, you can solve it there. And then once you're done finding that solution, at the end of it, you remove the freedom again and then find the result back down where you started. In this case, we free the variables x and y, right? You're not imposing g equals to k. We're just letting g be basically a variable k, working out the inverse function theorem at the end of it, setting k equal to what it is. So that's why people will tell you once you've proved the inverse function theorem, you automatically get the implicit function theorem because of this argument. So if I do find a day to bother you with these things, it will suffice for us to just prove the inverse function theorem. So, did I ever tell you the story about let the boy be? No? No. Friend Crazy Paul. When he was a little boy, he went to his old folks' home, and there's this guy. He was in a wheelchair, and he was like strapped in there, and like he's like, little boy, come here. Paul's like, okay. He's like 10 or whatever. He goes, and the guy's like, I just want to walk. I just want to be free. I just want to leave this place. Can you just let me go? Just loose my feet. So Paul, he's like, he's a grown man. He should be free. So he goes down. He starts to free the man's whatever ankle straps or whatever. And he said as he was doing it, the orderly came and tackled him. And then as he's on the floor being tackled by the orderly, the man is sitting in the wheelchair going, "Let the boy be! Let the boy be!" I still remember this story. It was an awesome story. That is just one of the many stories of the Crazy Paul. Oh, you can hit it. I guess that doesn't have much to do with advanced.